Well, let me just say a few words. First of all, this is an embarrassment because I've never said Jenny's last name out loud. So I'm going to say Jennie D from SUNY at Old Westbrook, a campus that didn't exist when I was young and riding my bicycle around in Nassau County. And she's going to talk to us about adapting SIMIODE modeling scenarios for calculus, which is a topic of great interest. We have found that as we run SIMIODE activities about differential equations, people want to not just move it into calculus 2, where there are differential equation issues, but as Jenny's talking about, into calculus 1. And we all know that modeling is good for all students. And so taking resources in A and putting them in A prime or B is good. So Jenny, you're on.
Great, thanks, Brian. So what I'm going to do is I'm going to run through 2 of the SIMIODE scenarios that I modified specifically for Calculus 1. And if anyone was in any other sessions with me, you know that I am much too beholden to the traditional syllabus of math courses. And I love the symbolic manipulation. So I have struggled with trying to get modeling into classes because of the time constraints, because I really do love, implicit differentiation and all of that. So anyways, so I did want to incorporate, oops, somehow my screen share stopped. Oh, what happened there? Okay. So I did want to incorporate into Calculus 1 on a time constraint. So I felt a little bit, I didn't want to necessarily have like a class on differential equations and then another class on like doing a lab, I called them labs, not modeling scenarios. I don't know if I should have done that, but that's what I did. So here's what I did is here's the first modeling scenario that I modified. And as you can see, this one, I keep losing my share power somehow. Okay. As you can see, this is one of Brian Winkle's scenarios. This is the oil slick scenario. Look at, we good? Okay. And yes. If you look at the parts here is even just part A of this modeling scenario, it says build a model. Okay, so the students have to know how to build a model in order to do this scenario. Okay, so that's a problem for me in Calculus 1 because I really didn't want to take a whole separate day to teach them differential equations and modeling. Okay, and what I wanted to do was somehow find a way to like rejigger this scenario and make it so that the students kind of learned what a differential equation is by the process of going through the modeling scenario. I also kind of played a couple of, little just creative games with just the wording a little bit, which is not really mathematical comments at all. So for example, when it says, from time to time, but irregularly, a helicopter is dispatched. I thought from a student's perspective, well, why is it irregular? Like, what's the helicopter's problem? Like, why can't it go on a regular schedule? And then, here we've got the measurements. As you can see, each measurement is 10 minutes later. So it goes up and it gives you 2 measurements, the size initially and the size after 10 minutes, but it doesn't actually give you when those photos were taken. So I was thinking from a student's perspective, well, why wouldn't you know when they were taken? Is there a reason? So there's a couple of different things that I built into my version of the oil slick scenario. One is I just did a little bit of narrative and I explained, oh, well, the reason the helicopter goes up at an irregular pace is because you have family obligations. And the reason why you don't have a particular, T value for your time measurements is because the data is corrupt and you didn't file any paperwork, So I put some of those kind of fun things in there just to explain to the students where those mishaps come in and why the data is not perfect, and that's what happens in real life. As to the data collection part of it, I did build in what I thought was more of like unique, I built in a uniqueness factor into the lab, where I basically asked the students to estimate what would happen on trip number 8. And the students just put their own values in there as long as they were kind of roughly in accordance with the previous. And then the first thing that they did was they calculated the difference equation in order to estimate the derivative. And then once you have the area and the derivative of the area, then the students, well, I'm just going to skip this part for now, but I'll come back to it, is they just used one of these little calculators online in order to get, you know, roughly the best fit line, and that gives you your differential equation. And what I did here in this section is, like I said, I did not tell the students what a differential equation was before I gave them this lab. And what I actually did in the lab was to show them, well, let's do the very first differential equation that everyone has ever seen in their life, which is the derivative of e to the 2x is 2 times e to the 2x. So I had the students kind of discover the exponential model by doing this little exercise of basically guess and check for the differential equation so that they could learn what a differential equation is. And then lo and behold, the stuff that we got from the best fit line, oh, wow, that is a differential equation. So then I had them, now the actual differential equation is constant coefficient linear, whereas up here I had them do guess and check for exponential model. So down below, I just had them do more guess and check, say, okay, now the model's more complicated. Instead of just being a regular exponential, it's got an extra, you know, plus, you know, y prime is equal to ky plus b. And now there's a plus b in there. So how do we solve that? So I did a little bit more of like guess and check to sort of emphasize to the student that you have to get the left hand of the differential equation equal to the right hand side. So that's all actually built into this lab. So like I said, I didn't actually lecture about differential equations before giving them this activity. I just gave them this activity hoping that they would discover what a differential equation was by going through it. I thought that the students were going to get stuck at some point, you know, that I previously described. They were actually good up to that point. The number one question that I got from the students is, once we got to this point of solving the differential equation and we got to the 5th part of actually, you know, using the function to make predictions, the students were like, oh, I can use my function now, right, professor? And they were kind of excited about it. And I really thought that they were going to get stuck at a prior, you know, point of the lab, but it really went quite well. I put some additional things in here, like suppose that nobody cleans up the oil spill. In order to give this, because, you know, this is calculus 1, so you're doing a lot of, you know, limits, and I wanted to make sure that the students really understood what limits, you know, mean. So I said, okay, nobody picks up the oil spill, and what that means is the limit as t goes to infinity. So what does the area of the oil spill approach? And then I built in some questions about how much it costs. So, you know, trying to make this, part of what I tried to build into this oil slick lab was not just you know, a prediction about how big the oil slick is, but turn it into, you know, posing it as an environmental cleanup problem, which is how much resources would you need to clean up, you know, X number of square miles of oil. So that's also something that I wanted to build in, was to try and motivate the students as to why they would care about this oil. So, like, not just simply, let's just watch it get bigger and bigger and, you know, I don't know, cross our fingers or something, but, you know, let's actually think about how we would solve the problem. How would you clean it up? How much money would it cost? You know, how much people would you need? And then I did put in sort of open-ended part towards the bottom, because by this time, the student has now gone through what has essentially been a very guided way of doing the modeling, where they learned what a differential equation was by doing this exercise. But then for the final question, I can ask them, okay, well, what types of things do you think would happen in real life that weren't reflected in this lab exercise? And I got all sorts of great answers, like students saying that maybe the wind could blow and the oil slick could spread in some sort of way, and that increases your cost. Or maybe you've got some ducks that are flying through and it spreads the oil spill, or other like environmental factors. So I did try and sort of reframe the oil slick scenario, not only to teach the students differential equations sort of in a first contact type of way, but also to get them to think about how it would affect people's actual jobs, how much money things would cost, what kind of ramifications, extra types of environmental difficulties would, change things up and present problems for modifying the scenario. Okay, so that is, this was what I called lab number 1, is I did the oil slick lab. The next one that I did was lab number 2. And for this one, I focused on modeling cancer growth. And this is a pre-existing modeling scenario from Ju Wang at Union College. And if you scroll through this SIMIODE lab real quick, you can see that it gets pretty serious really fast. So how am I going to do this with Calculus 1 students? That's what I'm thinking about. So first of all, she introduces the exponential growth, and it says, determine the maximum tumor size. Then it's the power law, again, determine the maximum tumor size. Then it goes straight into von Butterfly, if I'm pronouncing that correctly. Here you can see the solution to the differential equation is given, but it says determine maximum tumor size. And then it goes into logistic model, again, determine maximum tumor size. And then it goes into a Gompertz model. And then there's a model fitting, basically to decide which one of these models fits the scenario best. And there's a cute little diagram here to show all of the different models that you could possibly use to treat the cancer growth scenario. So down here, there's a bit of Euler's method, which I did not include in my Calculus 1, but I did do, as you'll see, I did do a little bit of the parameter estimation. I was able to build that part of it into my version. Okay, so let me just flip on over here to my version. So this is the same SIMIODE modeling scenario, but this is specifically designed for Calculus 1. And you'll see the changes and the differences as we go through. So the very first thing is, of course, in the previous version, it just said, exponential model, and then it goes on to the power law model, and then it goes on to the next model. But of course, my students don't know what the exponential model is. So I just started with that. And this was my lab number 2. So actually my lab number 1 was the oil slick, where they already had the exponential model in there. So this first part was sort of based on some of the work that we had done with the oil slick model, is assuming that the student had learned at that point what the exponential model is. And then immediately we show why the exponential model is bad. Well, that means that the tumor is going to grow to infinity. Well, that's bad. That's also physically impossible. So how can we modify this? So in order to introduce the next model, what I did here was I tried to motivate it using the fact that, the growth of the tumor would go to infinity, to say, okay, how can we change the model to make it more realistic? So then I did model number 2. For this one, like I said in the previous, in the original version, in Ju Wang's version, they included the solution to the differential equation. So I figured, okay, if my calculus students don't know any differential equations, what I can do is I can provide the solution to the differential equation as well, but I can have them actually check that it solves the differential equation just like you would do on the first day of differential equation. So that's a lot of my approach here, is to try and think to myself, if I was teaching exactly this lab on the first day of differential equations before they know anything, and the only thing that they remember is basic stuff from Calculus 1, how would I introduce, this topic? And then I go into the Gompertz model. And here again, it's a modification of the previous model. I had them sort of, yes, the solution is given to them, but at least they can check that it actually does solve the model. And then we do the limit as t goes to infinity to figure out the maximum tumor size. And lo and behold, finally, we have a tumor that does not grow to infinity. So that's good. And then I love this little diagram, so I included it in the version, even though my students did not, actually do all of these models, but I wanted to give them an appreciation for the variety of different models that could potentially come up, maybe to pique interest for future topics. And then I put in towards the end this model fitting, because they did do the least squares fitting in the first lab. This is something that naturally built on what we had done in the oil slick lab, and to do it now here, instead of being a linear fit, this is a different, type of a function here, where it's more like a logistic model. And so this really built on well what we had done in the previous lab. So what I did with this one is, again, I had them use like an online calculator to do the fitting. And what I had done here was I just created a Desmos lab, and as interactive thingamajig. And as you can see, most of the data is put in there. I think that I probably left out a few data points. That way the students don't have to spend an hour typing in the data. They can just do a couple to get the hang of it. And as you can see, the two different models that we're comparing here, they're definitely not doing a good job of modeling the data right now, because we haven't modified the parameters correctly. So what the students have to do is to try and figure out, like, what's the extra, letter that I have to put into this equation to make this model actually match up with the data. And then, of course, you would do that for each one of them, and then make a decision about which model matches the data better. Okay, so maybe that's sort of the end of it. There is a little bit extra in the SIMIODE modeling scenarios, showing a bit more on the tumor growth, and there's a little bit more extra information about treatments and how treatments are actually built into the model. I basically had that as my last couple of questions, which is simply to ask the question, well, if you had a treatment that was, like a simple treatment, how would that change the differential equation? And then I asked the students to reflect on, what type of analysis can you think of doing? What type of, similar for the oil slick scenario, where I kind of more open-endedly ask them, what sorts of things could you envision discovering in another lab that we could potentially do at some later point. Okay, so I think that's pretty much that pretty much summarizes my approach. I tried to make the scenarios actually introduce the differential equations without necessarily forcing myself to teach a class on differential equations first and then have them do the lab. This was literally just dive right in. Here's the lab, and then the students just go to work right away. And one of the things that I also did that I failed to mention for the oil slick lab, you might have remembered that I did have the students just put like custom data into this section. What I also did do was just made a little octave script so that as I'm, correcting the students' labs, calculates everything for me that they need in the lab, so that if everybody has different numbers, it can be very time consuming to grade, but this really made it nice and easy. So I did include in the SIMIODE modeling scenario post that this little script that will just simply, calculate the correct answers for each student's individual numbers. I feel like I've been talking for a while, so let me just pause and see if there's any questions.
Are there any questions here? I don't want to bring religion into this, but if you remember in the New Testament, St. Paul has this man named Saul has this opening and change of whole perspective on the way to Damascus, the road to Damascus. And Jennie just shared with us her change on the road to Damascus by saying, I don't normally do this, I don't do this. And here she was in a Calculus 1 class. How far after the derivative do you actually do this kind of model?
Oh yeah, so as soon as they knew all of the rules, so right after, oh, you know what? No, what did we do? So we made it all the way through product rule, chain rule, and then we did one section on related rates right before we did the oil slick scenario. So yeah.
So what you see is a person who went through just the basic stuff, right? The hand stuff with Calculus 1 students, and then jump into a differential equation. This is almost suicidal in some people's minds, I'm sure, But what she did, and we're very proud that she submitted and we published the adaptations for those, she actually brought it home to them so they can see beyond their calculus that they're doing right now, and the power of rates of change, basically, is what she's talking about in one setting that's as diverse as you can get, oil spreads and studying medicine and cancer. And what was your students' reactions?
So one of their biggest reactions is this is a lot of work. Okay. So there's that. But as far as interacting with the labs, they were really just on board. I kind of thought that I was going to have to like convince them or kind of cajole them to kind of like get, into the mode of it, but they just started working. And by the time we got to the middle of the session, I should probably say, I have 1.5 hour classes. So if you wanted to do this, if you had a 50-minute class, probably 2 of them, but I have 1.5 hour classes. So I did 1 of them. So I did 1 class for each lab. That's it. And if the students were not able to finish, I gave them some extra time. But all in all, I thought the students really responded well. Questions from
audience, anyone?
Mark?
Well, good morning, Jennie. I've really enjoyed your presentation. I've often downloaded, well, not often, I've downloaded quite a few tutorials from SIMIODE, and I've always been at a loss at how to adapt them for my students, and you've given me some really great ideas this morning. I'm very interested in the question about how the oil slick spreads in the limit that t goes towards infinity. Before I ask you my question, can I ask, what answers do students give to that?
Well, I probably should say that they built the model first and they solved the differential equation first. It wasn't a conjecture that they made beforehand, but maybe that's something that I should have built in, to this, which is to have them maybe conjecture what they think it'll go to and then see what the model, says it goes to. So that's actually a different kind of approach that I didn't do. But what I had them do was I had them solve the differential equation and then take the solution and figure out what the solution goes to.
So I'm guessing that most students said that as t goes towards infinity, the area went to infinity. Is that what they said?
So this one was a linear first order constant coefficient. So if it was y prime is equal to ky minus b or plus b, I forget, it did go to the constant of like b over k or something, which is the equilibrium. But, you know, I felt that that was a really appropriate way to approach the material for Calculus 1, because the students are often annoyed by limits and they don't know what they're doing or what is the purpose of them. So, you know, having the limit as t goes to infinity for example, for the maximum tumor size, I mean, the fact that the tumor goes to, the tumor was the one that went to infinity, but the oil slick, you know, went to a finite number.
I guess I was just wondering if students argued that if you took a finite amount of oil, it spreads out, but then when you calculate the thickness of the layer, it would be so small that you couldn't see the oil slick, so therefore the answer was 0. The mathematical answer is not 0, but maybe the physical answer is 0. So there might be a difference between the mathematical answer and the physical answer.
Yeah, I think if that had come up, I think I probably would have expected it at the, you know, the final question that I asked them, like what different, you know, things could have happened in real life. That's not one that the students mentioned. A lot of them mentioned like environmental factors or, you know, boats going by or birds or something like that. But, you know, that's definitely something that I think if I had guided it a different way, I could probably build in an analysis, you know, like that. So I think it's actually a really good idea.
All right, thanks.
One thing you can do is model the spread of slime. Every teenage young lady I found out knows how to make slime. There's thousands of YouTubes on that, but you can make slime and let it just spread out. And we have a video on the SIMIODE YouTube, and you can collect data on the spread of slime, and eventually, you know, friction plays a role and it doesn't spread. I want to thank Jenny. We have to move on to the next section. And I particularly want to thank her for being courageous enough to jump into a differential equations notion with Calculus 1 students and show them the future. So thank you very much, Jenny.